Right. So we have stopped over here. So now we have everything. Okay, we have everything. We're going to assemble all our equations together, okay, to find the shear in the xy direction. So the shear in the xy direction, let me write this as the shear in the xy direction is equal to Vy over Iyy, right? Sorry, Izz Qz divided by T. So as you can see down here, it's easy to, I mean, Vy is pretty straightforward to find what is Vy. Izz also straight. The confusing part is what? The first moment of area, Qz. Okay. And T is not that difficult to know what is T, right? So from here, we know that Vy still remain the same. Then divide by Izz. So we have our Izz is equal to 2/3, right? 2/3 BC cubed. And then our QZ, which we have written down here, is 0.5 multiplied by B, right? Then you have C squared minus by Y squared, right? And then the thickness over here, did we find what is our thickness? Did I write what is our thickness over here? So not yet. So our thickness, as you can see, right, is perpendicular. The force that is perpendicular, or the geometry that's perpendicular to the applied force. So our applied force is over here. So this is Vy. So our thickness is equal to B. Okay, so thickness is equal to B. So this is our B. Okay, so we are going to simplify this term. The half down here, let me put it this way. Then later on, when I start doing stuff, you can see what's going on. Okay, so now we are just going to simplify the terms. Okay, so we can cross out the B, right? So this will be equal to Vy. I'm going to bring the 3 to the top. I'm going to bring the half to the bottom. 3/4, or I'll go, yep, 3/4, right? So you have C squared minus Y squared, right? And then this is equal to BC cubed, right? And then I'm going to declare note. Okay, so I'm going to make a bit of changes. Note that the cross-sectional area, right? The cross-sectional area A, I'm going to call A the cross-sectional area, is equal to B multiplied by 2C, right? So why multiply by 2C is because the height is what? C at the top, C at the bottom, so it's 2C. Okay, so this is equal to 2BC, right? So I'm going to rearrange this term until I get 2BC. So this is Vy 3 C squared minus Y squared. Okay, I'm going to take out the 2, right? I'm going to put a 2BC over here, right? So this will left with C squared, right? So if you remove the brackets, the denominator term is the same. So because of the note where area is equal to 2BC, so we are going to change this to Vy, right? 3/2 C squared minus by Y squared, right? And now this is equal to area C squared. And then we rearrange this again. You have 3/2A, right? Vy. And then we're going to have C squared over C squared minus by Y squared over C squared, right? So this will be equal to 3/2A, right? Vy bracket 1 minus by Y squared over C squared. Okay. So once again, what we can see down here, the y over here is the variable, right? It's our slider, right? If you look at this diagram over here, y is our what? Our slider. It will move up and down, move up and down. And the y prime is dependent on where your y is. Then from here, right, we know that the c is a what? Is a constant. The depth of the depth of the structure from the datum. Okay. So by looking at this equation down here, right, like what I highlighted earlier, right, that's where you know that this term over here, right, the greatest, right, it will always be less than or equal to 1. And when this term is equal to what? Is equal to 0, what will happen? Right, you will have your max. So tau max or tau xy max is equal to 3/2a multiplied by Vy when y is equal to 0. Because when y is equal to 0, this term over here will then be equal to 0. So that is your tau max. So now, if we were to sketch the distribution of the shear stress now, okay, so I'm going to take the cross section, and I have to write down one more rule for you guys. Okay, so if we were to sketch okay, so if we were to sketch the distribution of the shear stress, okay, now we are calculating the distribution now. Okay, we are not taking just force divided by area. Force divided by area is just the average. Okay, so this we are plotting the distribution. So we are going to say that this is our shear stress, right? And the y is our y. Right? So this is our y. This is at 0. Okay. So this is 1 point over here, and there's 1 point over here. Right? So what will happen, right? What will happen over here is when, if we look at this term over here, right? We look at this term, the shear xy. So we have created a function as 1 minus y squared over c squared, right? So now we realize that when y is equal to, so at this point over here, right? At this point over here, y is equal to c, right? And then at the bottom term over there, y is equal to minus c, right? So if y is equal to c, what you have is 1 minus 1 is equal to what? 0. So the shear stress at the extreme point will start from 0. And then when y is equal to 0, this is where we have our shear max is equal to 3/2 Vy. 3/2a multiplied by Vy. Okay. And then we sketch this because of the second order polynomial term of y squared over here is going to be set phase. And then it's reflected at the bottom. So that is the distribution of the what? Of the shear stress. And what we realize that Vmax or tau max, okay, what we realize that tau max occurs at the centroid of the entire structure. Okay. So from here, I'm going to write down rule number 4. But before we're going to write the rule number 4, this is the distribution. Okay. This will be the distribution of the shear stress. Okay. And now I'm going to write down rule number 4. Okay. So rule number 4. Oh, sorry. Some of you might be still copying. Are you okay? Are some of you copying, or are you okay? Or I can move on. Are you fine? Okay. I have no reply means you guys are okay. So rule number 4. Is one of the most important rule. Okay. Is that the first moment of area the first moment of area region, right, cannot cross or intersect the centroid. Okay, so this is rule number 4. Okay, so some of you, Eugene, what do you mean by that? What do you mean, like, it's so abstract? Yes or no? What do I mean by that? So now, if we're going to look at a cross section, okay, so this is Y, this is Z, and we are going to look at a T cross section. Right? Okay. So this is our T cross section. I'm going to copy. I'm going to draw the centroid first. So the centroid is somewhere around here. So this is our ZZ. ZZ is our centroid. Okay. So I'm going to have this. I'm going to copy, and we're going to have a few cases. Okay. So now, if we know that the shear force is over here, Vy, right? And the area of interest is here. Oh, sorry, not the area. I want to find out what is the stresses at the point over here. So I'm going to call this point alpha. Right? This is our point alpha. So the area to consider is this area. This one is straightforward. So the analysis will start from what? Will start from y max, right? Y variable is max. So this is the area that we're interested in. This is how you calculate your first moment of area. Okay. Okay. Now, if, right, now what will happen if I'm going to do some changes now. So same thing. Right, same thing.
Hey Eugene, quick question for the problems. For now, you're gonna give us the location of the centroid?
No, you're going to find.
Okay.
I'm going to teach you how to find. Okay, so now, so this is one scenario, right? And then from the next scenario, what will happen if Vy is here, and then the point of interest is going to be at alpha? What is the first moment of area that you're going to take? Okay, so we look at our rules. Okay, so I want you to look at the rule. So rule number 1. Right, rule number 1. So now it's confusing now. Now Vy is over there, right? So now rule number 1 is what? Rule number 1 is V and I, right? V and I are constant. That's rule number 1, right? And then rule number 2, the datum is at the centroid. Rule number 3 is the analysis